So the topic of my talk lies in the intersection of the ergodic theory of dynamical systems and the analysis in sublet spaces. So this work is a joint work with Alexander Profetov from Steklov Institute and CNRS, and Sebastian Goizel from Institute of Mathematics of RAM. So, what is the setting? I studied the diffeomorphisms of compact Riemannian manifolds, just infinity diffeomorphisms. But we put but we assume that the diffeomorphism has a special property that we call the analysis property. That is, we assume that the tangent space to our manifold M at any point x is decomposed into the sum of the unstable and the stable space. In the unstable subspace, the vectors expand, and in the stable direction, they uniformly shrinking. So lambda, the parameter lambda is called the utilization parameter, and these subspaces are called the unstable and the stable subspaces respectively. So these subspaces are integrable, and the manifolds, the resulting manifolds are called the unstable and the stable manifolds. Well, these manifolds depend continuously on x, but let me switch to a simplest example. A simplest example of the analysis of diffeomorphism is the famous Arnold's cat map. That is, you take a torus that is just f square mod of z square, and apply a matrix 2, 1, 1, 1. This matrix induces a diffeomorphism on the torus, and for example, at 0 we have two eigenspaces, or just the eigenspaces of this, two eigenvectors of this matrix. One vector is expanding and another vector is shrinking. So, well, why this map is called Arnold's cat map? Because there's a famous picture when you draw a cat in this square, and then it distorts along the square, and it smashes and distorts, and it's really funny, mixing of all types. Well, yes, this property of smashing and distortion is called mixing. I propose here a topological definition. A diffeomorphism T of compact manifold is topologically mixing if for any two non-empty subsets V prime and V double prime, so there is some natural numbers, since that the intersection of Tn V prime and V double prime is non-empty. For example, you have sugar in a teacup, and you mix it by a spoon, and the claim is that in any region of the cup there is some sugar after some iterations. Well, but this is a wrong definition that we'll need. So, what is the problem? The problem is the following. Let T be a topological mixing and also diffeomorphism, and I consider through any point x in our manifold as two submanifolds that we call unstable and the stable ones. Let us fix a ball in the unstable in the unstable manifold of the point x of radius 1. The radius is assumed in terms of Riemannian metric. Let me expand this ball under the iterations of t. So when we apply n iterations of our map t, we get a huge ball. So let me consider the averages of, for example, continuous function f on this huge ball, and normalize it by the volume of this ball. It turns out that these averages converge uniformly to the average of the function f with respect to a special measure that is called the measure of maximum entropy. This is not an absolutely continuous measure. It is rather singular, but nevertheless we have some measure that with respect to which these unstable manifolds are equidistributed. So, well, how to construct the measure of maximum entropy? First of all, you take a family of leafwise measures on unstable manifolds with the following properties. The first property is the uniform expansion, is that we apply a map T, and the measure of the iterated set can be expressed as follows. And the second property is the invariance under the stable holonomy. Well, the main feature of the anosov diffeomorphism is the presence of the lamination structure. That is, locally the manifold is just cut into the union of unstable and the stable manifolds. And here we have some homomorphism H from one leaf to another. We assume that the measure of this subset is the same as the subset of the same as the measure of the foliated set. Okay. In the same way, we can construct the stable, the measures on the stable foliation, and then just take its product and get the measure of maximal entropy. Let's skip a bit further. Well, so we have this convergence. But the main question of my talk is the following one. What can be said about the error terms of the asymptotics of the left part of this convergence? Can we write the next terms of this convergence? We apply some generalization of the construction of the measure of maximum entropy. That is, we take some functionals on piecewise infinity subsets. So infinity, I mean very maybe C100, for example, and assume that they satisfy the property of holonomy invariance. Well, these functions are not positive; they are even complex functions in general. Well, and we would like to give the precise asymptotics in terms of these finitely-additive measures. So, how this can be done? So we endow the space of finitely-additive measures with some kind of analytic structure. That is, the idea is the following: we consider the space of all du dimensional differential forms. No, du dimensional of differential forms of degree du, where du is the dimension of the unstable foliation. And then we apply just the image of this form by the map T, and normalize it in such a way, in this way. So the task is to endow the space of differential forms with an appropriate norm, so that this operator would have a nice spectrum. Well, what I mean by a nice spectrum? I mean that this operator is a quasi-compact operator. Instead of formal definition that I give here, let me switch to this picture. The spectrum of this operator is organized in the following way. The norm of this operator doesn't exceed some number rho, which is, well, the big circle. The operator can, I state that the operator, well, the operator, for example, if L acts on some Banach space, the Banach space is represented as a direct sum. The restriction, this direct sum on the restriction to y first is the restriction of the operator L to the subspace y1 has a discrete spectrum even finite. There are a finite number of eigenvalues in this annulus, in this white annulus. Finite number of eigenvalues with finite multiplicities. And there is an operator y2 with a small enough norm. Here the spectrum is continuous, but this won't matter. Well, how we define the appropriate norm? It is not. It's not good to define the norm in a direct way, because if we just put the C K norm, for example, into space, it will be larger and larger depending on K, because our map is an expanded map, for example, in the unstable direction, and the norm will grow and grow, and there is no chance to obtain a sort of compact or quasi-compact operator. So how we define the norm? Well, the first point is the following. We would like to measure or to integrate the characteristic functions of nice sets. And the second, we want this. We still want these forms be regular in the stable and the unstable direction. So I'm switching to the definition of the norms. So first, let me introduce the fractional Sobolev space, WSP, that is the space of all LP functions, say that this expression is finite. This space is invariant under diffeomorphism, so one can successfully define the space on smooth manifolds using the partition of unity. But we have to work with the subgroup space with a very low regularity. That is, we ask for the following series of inequalities. Okay, so we assume that S is less than 1 over P. Well, some we come with norms. The norm is the norm on the binary space B is a sort of weak norm. So these forms are maybe not the forms but the currents. Nevertheless, so this is the first part of the norm lets us to integrate the integrals of characteristic functions of nice sets. And the second part, the stable part, is needed for some regularity along the stable foliation. Here is written the leader derivative of the form. Well, so this is the norm. It turns out that if we have this inequality, here is written the Jacobian of the map reduced to unstable direction. Then the operator in this space has a nice spectrum. Moreover, the top eigenvalue has is equal to 1, and there are no eigenvalues on this circle. Well, but then we want, well, how much do I have? Well, I don't think I have much time. Well, but there is another abstraction that we need really holonomy invariant objects. That these conditions yield some extra restrictions on the spectrum. Well, and on the choice of the space as well. So, in one of the, well, let me show the picture. Well, we previously have obtained the finite dimensional subspace that is generated by root subspaces of these eigenvalues. But we should cut out this region and leave only those eigenvalues that are close enough to 1. So this subspace of differential forms will give us these holonomy invariant pairs. On the other hand, one can consider the measures on the stable leaves. Well, yes, we consider the measures on the stable leaves and apply the operator defined in the following way. And give another finitely dimensional space. These spaces are dual to each other, and the pairing is given just by the product of this. You may call it finitely-additive measures, or you may call it just holonomy invariant currents, as you wish. So this gives us the pair. Okay. Thus, so we almost came to the main theorem of the talk. So assume we have a function of C2 and C2 on the whole manifold, and let us integrate and let us consider these normalized averages. We have the basis in the space of finitely-additive measures on the unstable leaves and on the stable leaves. These bases are dual to each other. So we have a decomposition of this integral in the following sum. Each term of this sum is the product of two things. the second thing doesn't depend on the set B. It is just the invariant distribution or generalized function on the whole manifold. And the first one is a generalized measure on the generalized finitely-additive measure on this big iterated ball. The growth of these measures is given in terms of the spectrum of the operator that we discussed earlier. So, well, I think that's all. Thank you for your attention. Thank you very much.
Some questions to this last talk. Дмитрий, можете показать, что происходит с этим, который получается один сжимаем, да, получается?
Geometrically, the diffeomorphism T shrinks in one dimension and expands in another direction at any point. Luckily, it's like this. Well, and
in limit we have.
Well, in limit, there are two features. The classical ergodic theorem for nodes of diffeomorphism tells that we consider a function on the whole manifold and consider such a sum. This converges to the invariant measure, but we consider another variable about the word. I consider another situation. Well, maybe more simple geometric maybe a more simple example that shows the feature is the following. For example, we have a torus, well, and we have, for example, map 2111 or some distorted. And we have a vector field. Well, I take a long trajectory of this vector field and consider the average of the function over this. Here the situation is more simple because we have a flow on the torus. But here we don't have any dynamics on these leaves. In these features there are two dynamics. The dynamic generated by the flow and the so-called renormalization dynamics that is given by the nodes of diffeomorphism. This expression has a little bit different behavior compared to the ergodic sums according to the diffeomorphism as well. For example, for this expression, we don't have a central limit theorem, for example. The limit behavior is slowly chaotic.
Some other questions? If not, let us send speaker.